This conference will now be recorded.
So, very good evening, all. Today, we will be learning about Bohr's atomic model. So far, we had learned what was Rutherford's model, which was given on the basis of the results obtained in alpha particle scattering experiment from the gold foil. So, I'll just recap a little bit because there is correlation between these two models of atomic structure. Like Rutherford's model, Rutherford was actually like Bohr was like accepting Rutherford's model up to some extent, and then there was already quantum concept of radiation. So he put together this Rutherford's atomic structure and quantum concept, and then he had given a model which was able to explain certain things which Rutherford was not able to do that. Okay, so I'll just tell you what are the like postulates or the points in the Rutherford model first, and we'll just recap briefly what were the limitations in the Rutherford's model, so that Bohr had to again propose another model or better model. So see, in Rutherford's model, atom consists of a small and massive center in which the entire positive charge and almost the whole mass of the atom was concentrated. So are concentrated. So this is the first postulate in Rutherford model. So this is called nucleus, idea of a nucleus. Okay, this postulate gives the idea of nucleus. Then this nucleus is surrounded by, so nucleus was surrounded by suitable number of electrons, so that their negative charges are equal to the total positive charges on the nucleus. Okay, so and the atom as a whole will be electrically neutral. So this is the second postulate. So how electrons were distributed, how positive charge in the nucleus was distributed, this is what actually explained in this. So Rutherford states that nucleus is surrounded by a suitable number of electrons, so that the atom will be electrically neutral. Okay, this was the second postulate, and third postulate was that how electrons will be orbiting around the nucleus. So he states this was actually classical idea of classical theory. Classical theory. According to classical theory, electrons revolve around nucleus in various orbits, just like planet do around the sun. Okay. So what we have seen, sun is at the like at any of the foci, two foci, and planets will be revolving in elliptic orbit around the sun. So Rutherford states that electrons also will do the same thing, but he did not specify which orbits will be allowed or not. He states that all orbits are allowed. All orbits are allowed. Like electron can take any orbit to revolve around the nucleus. Okay, so this is where the problem was. Basically, this is the problem. Okay, so we have seen then the limitations in the Rutherford's model. Rutherford's model could not explain the stability of the atom. See, in the third postulate, what Rutherford states that electrons can orbit in any possible orbit. But it is not true because electrons are charged particles. When they revolve around the nucleus, then they have certain acceleration, that is centripetal acceleration, and due to acceleration, so any charged particle, accelerated charged particle, charged particle radiates, radiates, okay, radiates energy. That means it emits energy, release energy in terms of radiation. And that's how an electron, which is suppose, okay, we'll show it here. Suppose the electron is somewhere here in the beginning, and when it starts rotating about the nucleus, then due to acceleration, it will emit its energy in terms of some radiation h nu. Okay, and since it is releasing energy, it will lose its energy, and slowly you will see the radius of the orbit will decrease, and finally it will lose the whole energy and fall onto nucleus. And that's how there is, like, there will not be any stationary orbit, or there will be no atom as such. Okay, so this is said that this is called actually stability, instability of the orbit. So it cannot speak about or cannot explain the stability of the atomic structure or stability of the orbit. So then another drawback also was there, that is radiation. See, in case of in this, like, according to this model of Rutherford, electron is actually releasing energy continuously. So you must be getting continuous atomic spectrum according to this model, Rutherford's atomic model. But what we see, actually hydrogen atom exhibits discrete spectrum. Okay, so these were two basic drawbacks or main drawbacks to just explain these things, just to uh, explain the stability of the atom and discrete nature of the atomic spectrum. Bohr has actually given a model where he actually accepts the nucleus concept. Rutherford models he accepts partly, and he accepted two things. Actually, Bohr accepted Rutherford's model partly, and he borrowed the concept of quantum nature quantum nature of radiation, or quantum concept of radiation. In other words, we can say quantum concept of radiation. So combining this, so this quantum concept of radiation was given by Planck, actually given by Max Planck. So when he was not able to explain the Planck, when Max Planck, when he could not explain the spectrum of black body radiation, then he had postulated this. Okay, what is that? That radiations are actually pockets of energy. They are discrete quantity. They can behave as discrete quantities. So suppose we were seeing already light. Light is also radiation. So we first took this as ray, then we took that as wave. Now we are taking the radiation of the light as light composed of discrete pockets of energy, which are called photons. So this is the thing which we have used even in case of photoelectric effect also. So here we have to use the quantum concept of radiation, and then just combining these two concepts like Rutherford's model, nucleus concept, and the quantum concept of radiation. Bohr had postulated the there are actually four postulates in Bohr atomic model. So we'll discuss one by one. First is the nuclear concept. An atom consists of a small and massive central core, as Rutherford's model stated, called the nucleus, around which electrons revolve. The centripetal force required by required for this rotation is provided by electrostatic attraction between nucleus and electron. So this we know. So this we know from Rutherford's model. Then the second postulate is that this is called quantum condition, which is very famous, and this will actually explain the stability of the orbit. Okay, this is the condition for allowed orbits. So of all possible circular orbits allowed by the classical theory, so Rutherford had postulated atomic models according to classical theory. Now Bohr had actually come up with quantum theory, and this condition will be given by, like, the condition for stable orbit will be given by this condition. The electrons are permitted to circulate only in those orbits for which the angular momentum of an electron is an integral multiple of h by 2 pi. So what is angular momentum? So we know angular momentum. So here it is stated that those orbits are only allowed, not all the orbits. Those orbits are only allowed for which angular momentum. So angular momentum is given by m v r for a particular orbit having radius r. If suppose there is an orbit, suppose this is the orbit which has radius r. So this orbit is allowed. Electron can orbit or revolve around the nucleus in this orbit only when the angular momentum of that electron in this particular orbit, this is mvr. So this has to be equal to the integral multiple of so is equal to integral multiple of h cross, which is written as h by 2 pi. Okay, I'll write it in brief. So angular momentum mvr we have already discussed before. How mvr comes, you have to go back and read the rotational mechanics. So mvr has to be integral multiple, suppose this is the integer, h by 2 pi. Okay, this is the condition for stable orbit or allowed orbit. So this is called quantum condition. This condition is called quantum condition. So this condition is called quantum condition. So I'll tell you what are these. N is actually integer. These are actually integers. Then H is Planck's constant. Planck's constant. Okay, this is Planck constant. We know what is Planck constant. It has a value 6.63 into 10 to the power minus 34 joule second. This we know. Okay, we have used several times so far. So angular momentum, we can briefly we can write L is equal to nh by 2 pi. L is the angular momentum. Suppose I think it is for nth orbit, so ln is equal to nh by 2 pi, where n can be any integer like 1, 2, 3, 4, 5, 6, etc. Okay, etc. So it can go like that. So these are integers. N is actually integer, or this we can write in elaborate way. mv rn also you can write. Rn means nth, like this is the radius of the nth orbit suppose. So this is ns by 2 pi. So this is the Bohr's quantum condition. Okay, so here see L means this is angular momentum, n is the integer number as you know, and this is Planck constant. Okay, so this is called famous Bohr's quantum condition. Okay, Bohr's, this is called Bohr's quantum condition. This is called Bohr's quantum condition. Condition. Okay, so first postulate was Rutherford's postulate, first postulate only, which is giving the nuclear concept. Okay, and then quantum condition we have learned mvrn is equal to nh by 2 pi. This is Bohr's quantum condition, which gives the which states about allowed orbits for electrons. Okay, this, see in Rutherford's model, we he thought electrons can take any orbit to revolve around the nucleus, but in this case electrons are, see, electrons are allowed to revolve around certain orbits for which this condition is satisfied. Okay, this is called Bohr's quantum condition. Okay, now we'll go for the third condition. So I'll just write it here. The condition mv rn is equal to nh by 2 pi. This is Bohr's quantum condition. So now see, the problem was there that in Rutherford's model, that it was not able to explain the stability of the atom. Now see, in combination of this and this, the stability of atom can be explained very well. See, while revolving in the permitted orbits, an electron does not radiate energy. So this is the point. See, if electrons revolve around the nucleus, it has to radiate energy, because they will be accelerated charge particle will definitely radiate energy and then fall into nucleus gradually. But Bohr's quantum condition states that there are certain orbits. This is a magic. This is the actually, what to say, this is the magic by nature, that there are certain orbits, if electrons revolve around the nucleus, there will be no radiation of energy. So these orbits are called stationary orbit, and condition for stationary orbit is this one. This is the condition. Bohr's quantum condition is the condition for stationary orbits. So while revolving in the permitted orbits, an electron does not radiate energy. These non-radiating orbits are called stationary orbit. We will be using this word stationary state, stationary orbit, this these things many times. So you have to just remember, by stationary states we mean to say various orbit. Okay, various stationary orbit. Now look what is this n is saying. N is actually giving your principal quantum number here. Principal principal quantum number. Principal quantum number, as you have learnt in your chemistry, might be so principal quantum number. So you might have learnt in your chemistry classes also. This principal quantum number is denoted by n. So see here, n is equal to first means 1 means the first orbit, n is equal to 2 means second orbit, n is equal to 3 means third orbit, like that. Okay. So all right. Now we have got the stationary condition, or a stability of the atom can be explained. But what was the another drawback, which, like, what was the another case or another phenomenon which Rutherford's atomic model could not explain? That was the atomic spectra, discrete discrete atomic spectra. Okay, so that is given by that is actually explained or given by the fourth postulate of Bohr's atomic model. See, what is the fourth postulate? An atom can emit or absorb energy only when it makes only okay so only when it makes a transition from a stationary orbit to another stationary orbit. I'll explain this in detail. Let me tell you one more thing. Like, once more, this postulate: an atom can emit or absorbs energy. See, we had already established the stationary states of atomic orbits. Okay, or stationary orbit we have already discussed. That means atom is now, at least atom, the existence of the atom can be explained, the stability of the atom can be explained. Now how we can explain the discrete nature of energy? See, you have stated that here, see, electrons will not radiate energy when they are revolving in their permitted orbit. Those are called non-radiating orbits or stationary orbits. Then how do we get radiations? We'll get radiations only when they make transition from higher level to lower level. Okay, higher quantum, see, you can see from here, from higher quantum level or higher orbit to, see, n is equal to 3 is 1. Suppose n is equal to 3 is one stationary orbit, n is equal to 1 is another, sorry, n is equal to 2 is another one, n is equal to 3 is again another stationary orbit. So when an electron makes a transition from third orbit to second orbit, then see, each orbit has, we will learn very soon, each orbit has different energy. Like, this orbit has certain amount of energy, this orbit has even certain amount of energy. This is called greater energy, this is having greater energy. This has n is equal to 3. Third orbit has even higher energy. So when an electron revolve around this third orbit, like in this third orbit, then it has energy of the third orbit, suppose E3. So E3 is actually greater than E2. Here the energy of the second orbit is E2. So E3 is greater than E2. So when an electron, which is in the third stationary orbit, when it makes a transition or comes down to the second orbit, which has lower energy, so there will be a gap in energy, right? So electron was having E3 energy over here. Suppose 5 electron volt. Here it is 2 electron volt. I'm just taking, just supposing. So there is a gap, like there is a difference between the energy. So that difference in energy will be actually radiated, like that will be actually emitted by the electron as radiation. I hope it is clear to you. I'll just explain once again. See what the last postulate is saying, that an electron can emit or absorb energy only when it makes a transition from a stationary state or stationary orbit to another stationary orbit. See, I had explained that it is coming from n is equal to 3 to 2, but it so happens that it can go from n is equal to 2 second orbit to third orbit also. It can go to the here, from here to here. It can go to third orbit from second orbit. But how is it possible when the energy amounting of this, see, when it absorbs a radiation having energy which has, like, see, suppose the energy difference between these two orbits is this one, E3 minus E1, sorry, E2. So this much energy difference is there. So if there is a photon which has energy exactly this much, then an electron which is at second orbit can actually absorb this photon, okay, this photon, and then it can be permitted to go to the third orbit. So this thing is called excited. It is excited to third orbit. So when it goes from lower orbit to higher orbit, it absorbs energy. When it comes down from higher orbit to lower orbit, it emits the energy, and that energy actually is exactly equal to the difference between the energies between these two orbits. Okay, so suppose I have here, suppose I have an electron which is in the second orbit. It makes a transition to the first orbit, then energy difference will be emitted as a photon of frequency nu, which has energy h nu. Okay, so this is how. See, look here, the energy difference is definite. So this is a single number. It is not like 5 to 10. So this difference cannot be at 5 to 10 electron volt or something like that. Okay, this is just a number. That means it has a discrete nature. So you can get, see, one line having some color depending on the frequency. So suppose E1 and E2 are the energies associated with n is equal to 2 orbits and n is equal to 1 orbit. Then the frequency emitted by the atom will be, see, if that is nu, so nu can be obtained from this relationship. So from here we can obtain what will be the frequency emitted by an electron which is making a transition from E2, like energy level or orbit 2 to orbit 1. So it will be obtained by this E2 minus E1 divided by H. So this is actually called frequency condition. So from here we can understand what will be the wavelength or what will be the frequency emitted by a frequency of radiation emitted by an electron or atom. So there are many. Suppose in atom there will be, like, other orbits, an electron can go up to higher level, but that higher level is not a very stable level for them. Okay, so they they will try to come back to its lower energy level so that they will be able to stay happily in that state. Like any system in this universe always tries to minimize its energy so that it will be in a stable condition. So that's how electrons, like, you might be thinking, sir, there are orbits, stationary orbits, and these are all, like, all orbits are allowed according to quantum condition, Bohr's quantum condition. Like, if this is satisfied, there are many orbits. But why always, like, why it happens that electrons make transition? Because any system tries to tries to minimize its energy. So when some electrons are there in this orbit, so it has this much energy. When it is having here, so it has energy E2, which is less than E3, right? So electron will try to come back to its this orbit, and then when electron come back to its n is equal to 1 orbit, that means this is called ground state orbit. This is called ground state or lowest orbit. So this is the stable condition, or actually it has minimum energy when the electrons are there in the first orbit or ground state. So that's how electrons tries to make a transition from higher level to lower level. And not all radiations are in the visible level. There will be some radiations will be visible in the visible range. Some radiations will be in the infrared region, ultraviolet region, etc. Okay, so this is how the discrete nature of the atomic spectra can be explained up to certain extent by Bohr's quantum condition. Sorry, Bohr's atomic model. Okay, that is given by actually in combination of quantum condition and frequency condition. All right. So we have already learned what are the postulates of Bohr's atomic model, and these postulates are very important. And see, this Bohr's quantum condition is so important that it can explain. This is the only condition which explains the stability of the orbit and discreteness, discrete nature of the atomic spectrum. Okay. Now what we'll do, we'll use this Bohr's atomic model and try to understand the structure of hydrogen atom. In fact, we know somewhat, and now there are few things which we are going to calculate from here, applying Bohr's quantum condition. So by using Bohr's quantum condition or Bohr's atomic model, we'll try to calculate radius radius of various orbits of hydrogen atom, orbits of hydrogen atom. Then second thing, we'll try to calculate the speed of electrons in various orbits. Then we'll calculate total energy of hydrogen atom, total energy of hydrogen atom using Bohr's atomic model. Okay, Bohr's atomic model. So we'll basically what we'll do, we'll apply Bohr's atomic model to calculate radius of various Bohr orbits, various orbits in the hydrogen atom, then speed of the electron in various orbits, and then total energy of the hydrogen atom. So these are main, actually fundamental points in this Bohr's theory of hydrogen atom. And from here, after knowing total energy, we will be able to find out not only the energy of hydrogen atom, but there are certain hydrogen like atom also. For them also we will be able to calculate the energy, and we will be able to analyze the spectrum up to some extent. So let us today learn these fundamental things which are needed for analyzing atomic structure or atomic spectra of any, like of hydrogen and any hydrogen like atom. I'll tell you what are hydrogen like atom later. So we know hydrogen actually it has one electron and one proton, one electron and one proton. Okay, so this is a very simple atom in the periodic table. So we'll take the first Bohr's postulate. What was that? That there is a nucleus which has positive charge, and electrons will be orbiting in certain allowed orbits. So in this case, both in Bohr's model and Rutherford's atomic model, the orbit has been taken as circular orbit. Circular orbit. Circular orbit. So using this circular orbit and this particular postulate, see electron is here. Okay. In fact, size of positive charge and nucleus will be very tiny. So in general, let us take this nucleus has positive Z into E charge. Z is the atomic number. In general, I am taking now, and then I'll write everything for hydrogen atom, putting Z is equal to 1. See, electrons are revolving around the nucleus, and how do you get, like from where we get the centripetal acceleration? We get the centripetal force, that is mv square by r. I get, like this is supplied from the electrostatic attraction between electron and nucleus. So this we know. I'm just writing the modulus of that force, 1 by 4 pi epsilon naught r square, if this is r, z square, okay, z into minus ze, and so you will get a minus sign over here. So I'm just taking the positive part, like magnitude of that only, modulus of that. So you get here, write this as minus, okay, so that we get positive. So we get, see, r1 r, you can cancel it. So you get mv square is equal to z square by 4 pi epsilon naught, okay, divided by r. All right, so we'll just find out. So radius and speed, and then total energy. Total energy, let us write as En only. Okay, we'll write it. So we have got mv square is equal to z square by 4 pi epsilon naught r. So from here, look what we can write. We can write as r. R is equal to z square by 4 pi epsilon naught into v square. Okay, so we can write this. Okay, so we'll just give a name for this equation. Suppose this is equation number 1. Now look, we know from Bohr's quantum condition Qn condition, that mv r will be is equal to nh by 2 pi. So from here we can find out what is r. So nh by 2 pi. Here this h is Planck constant into mv. Now look what we can do. We have got equation number 2. So from equation 1 and 2, what we can write is z square by 4 pi epsilon naught v square is equal to nh by 2 pi m v. I think I have left the m over here, so there will be m over here, m here. Okay, so mv square. So now look, if we just equate these two, then we can strike this m off, and then from here also we can get the equation of v. Look, then from here v will be obtained as, so v is here, I'll just put it here. So z square by 4 pi epsilon naught. Okay, so I think it will be, let us do one thing. We'll just put this as k, so that we don't have to worry much. So k is 1 by 4 pi epsilon naught. Whenever possible, like whenever required, we will use this value. Let us write this as k only, so that things are a little bit simplified. K. So we get here v is equal to, look, now we can write it easily. V is equal to mv square. It is mv square gone, so v will be k z square by nh, and obviously here was 2, so 2 can be multiplied here. Okay, 2k z square by nh. Okay, so this is what we get from, okay, I think pi, I have just left out the pi here, I'm sorry, there will be a pi over here, nh by 2 pi, so there will be pi over here, so pi is here also. I'll write it freshly. What we get the expression for, if you just equate these two, this and this, 1 and 2, then what you get an expression for the speed of the electron in certain orbit. So we have got the radius, preliminary equation for radius. This one you can write, oh sorry, okay, let us write down v, what is v is equal to. So if you put, like if you equate these two, then what you get is 2 pi k z square by n into h n h. So you get nh. Okay, so let us take this as equation third. Then we'll just move on to the next page. So we are calculating radius, then speed and energy. Please keep patient. We'll complete this and then end the class. So we have already got from equation number 1. Look, we had got this equation for radius, but where there is a speed over here. So if we write what is speed, from this equation 3. So from equation 1 and 3, see, equation 1 was k z square by mv square. Okay, this is equation 1. And equation 3, what we have got now, k 2 pi k z square by nh, right? So this is the thing we have got, 2 pi k z square by nh. So this is equation number 3. Now if I put this equation 3 or the value of the speed over here, then see, putting v from 3 into equation 1 into 1, what we will get, r is equal to, see, if you put it here, k z square already there, and then m into v square means you'll get 2 pi k z square by n square, and sorry, n and h, and whole square of this. So if you simplify everything, what you get, you will get n square h square up, like in the numerator, and in the denominator you get 4 pi square m k z square. Okay, so if you just do the calculation or simplification in a cool brain, you will be able to get this. This is equation number 4, and this is the original, this is the actually the actual expression for radius. So we'll just go to the next page and write what is radius, expression for radius. So what we get, radius is n square h square, then 4 pi square mk k into z square. Okay, this is the expression we have got. This we have named it as 4. So this is the expression which gives you the radius of various Bohr orbits. So suppose I have various Bohr orbits, okay? Various Bohr orbits, various orbits. I'm sorry, we should not say Bohr orbit. We have various orbits. So these orbits, like what are the dimension of the orbit? Like how to what extent they are, like having, like what is the radius of this first, like n is, see, you can see one thing here, r is directly proportional to n square, where n is a principal quantum number. Okay, principal quantum number. All right, so look here, that this radius of Bohr orbits, like all orbits, radius of the orbits is actually depending on the principal quantum number, and how it varies, as n square, now if suppose you have n is equal to 3, then you will get r is equal to 3. Here you put 9 h square and all those things. Okay, so these are all constant. You look, I'll just do one thing. If I put all the values, see, all the values if we put, so what we get, look, I'll just do a simple alteration of this, or simple modification of this. See, if I take for hydrogen atom, for H atom, what are the things known? Z is equal to 1 for hydrogen atom. Okay, so this Z will go away. See, other things is like, say, K has a value 9 into 10 to the power 9. Okay, whatever unit with proper unit you have to put, and E has a value 1.6 into 10 to the power minus 19. Okay, this is Coulomb. Okay, the Planck constant has a value 6.63 into 10 to the power minus 34 joule into second. Then electron has mass 9.1 into 10 to the power minus 31 kg. So if you put, see, this value, this is 1 anyway. So if you put all the values, what you get, you will you'll get a very nice number. If you put z is equal to 1 and keep the n as it is, then you get this as, see, if you put this r is equal to 0, r0 means ground state. See, r is equal to, r0 means radius of the first Bohr orbit when I put n is equal to 1. Okay, this is called r0. This is called Bohr's orbit also. So it is h square by 4 pi epsilon, sorry, 4 pi square m k, and then z is square. If you put all the values whatever I stated now, so you get this as 5.529 into 10 to the power minus, yes, so minus 10 meter. Okay, that means nearly equal to 0.53 angstrom. So this is very, very important. You should remember this. See, I have got, see, if you just leave this part, for hydrogen atom I have got uh, the value of the first Bohr orbit r0. So then see, I can just replace this equation, saying that Rn means radius of any, like any orbit of hydrogen atom where z is equal to 1. So you put n is equal to n square as it is, and this part you have got r0. So you can write this relationship. So there will be a question in various competitive exam. They will give you that if r0 is, or if suppose uh like yeah, so they will give the the radius of the first Bohr orbit as r0. Then what will be the radius of the third Bohr orbit? So it will be actually 9r. Okay, third Bohr orbit will, radius of the third orbit will be n into r. So it is directly proportional to the square of the principal quantum number. Okay, so it is sometimes recommended to remember the value of first Bohr orbit. Okay, so we can replace this by saying n square r0, where r0 is 0.53 angstrom is the radius of radius of first Bohr orbit. First orbit, first orbit, first orbit, or which is called Bohr orbit actually. Bohr's orbit. Okay, this is the thing. Now see, there is speed. So we will just go to the speed. Now speed. We'll calculate speed. So we know from equation 3, maybe we know what is the expression for v, right? This one, equation 3. If we take this equation, 2 pi k z e square by nh, look here, 2 pi k z e square by nh. Okay, we'll just do a little bit of simplification. In this case, let us say z is equal to 1 for hydrogen atom. For h atom, z is equal to 1 if we put, then v is equal to 2 pi. Okay, let us just remove the z from here. Okay, okay, so now what we'll do, we'll just do some simplification. Let me tell you what to do. We'll just multiply See, n is there. So what we'll do, we'll just do this into, so this is a square by ch. C I'm just dividing and I'm multiplying. So this is c by n. Okay. So c I have just multiplied and in the numerator and denominator. That is what I have done. Otherwise things are all same. This is n, this is h. N I have put c by n. And look, this particular factor, okay, let me put the k also here. Then how does it look? 4 pi epsilon naught ch. If we just strike this out, then look, this factor is actually e square by 2 epsilon naught ch. This factor actually known as fine structure constant. It has a fixed value. This is called fine structure constant. See, e square, I'll write over here, 2 epsilon naught ch. This is called fine structure constant. Fine structure. This is very, very important in case of atomic spectra. Fine structure constant, and it has a fixed value. It has a fixed value. Okay, fixed value. Okay, so it has a fixed value. So it is denoted by alpha. It is denoted by alpha. It is denoted by alpha. Let us see. Alpha is actually e square by 2 epsilon naught ch, right? Ch. So this is alpha, fine structure constant. If we put the value of E, electronic charge, this thing, and H also, then what we get is actually, this will get as 1 over 136. 1 over 136. Okay. So look, if we know this value, we can write this V speed is equal to, see, this is alpha into c by n. This is fine structure constant we have written, and see the value of alpha is 137, 1 over 137. So what we can write actually, speed of any orbit will be like this, Vn. I can write this Vn. So if you want to write V, like speed of the electron in the ground state or in the first Bohr orbit, will be given by c by 137. This is, c is the speed of light. C is actually speed of light. Speed of light in vacuum. Light in vacuum. Okay, I'm writing back over 137. So this will give you actually the speed of electrons in the first Bohr orbit. For any orbit, then I can write the speed of electron in any orbit can be written as alpha into c by n, which I can write as c by 137 into n. Okay, or 137 of c by n. So if you write this is the general formula for calculating speed for any orbit, like for an electron which is revolving in any orbit. Now look, I'll calculate the total energy. So total energy En can be written as kinetic energy, sum of the kinetic energy plus potential energy. So I'm calculating the total energy. Total energy here. Energy of an hydrogen atom. Okay. So what is the kinetic energy? Kinetic energy can be written as half m v square. Okay. So if we just go back to the formula, like whatever we have got in terms of r and all, so you will be able to find out half m v square to be this kinetic energy. Okay, so let me just complete it with potential energy also plus potential energy. Okay, so see, I can write this kinetic energy as half mv square. So V, I know the value of V. If we put this, in fact, see, in general we'll write first. So it is given by k z square by 2r. Okay, kz square. So this is half mv square. So if you just go back to the third equation, like first and third equation, you will be able to find out what is the kinetic energy in terms of r, radius. And potential energy, how you can find out potential energy? We know how to calculate electrostatic potential energy, z square by 4 pi epsilon naught r. Okay, 4 pi epsilon naught r, epsilon 4 pi 1 by 4 pi epsilon, we have taken this as k, we have written this as k, here also we have written this as k. So look, this potential energy and kinetic energy, so this is k z square by r. Look here, actually the kinetic energy, see this kinetic energy, okay, kinetic energy, this is kz square by 2r, whereas the potential energy actually 2 times of kinetic energy. So this formula, you can remember this particular concept, that the potential energy of hydrogen atom is the twice of the kinetic energy of the, like, I mean to say, potential energy of electron in particular orbit is twice the kinetic energy of that electron in that particular orbit. So that is what I wanted to mean, but with a minus sign, obviously, with a minus sign. Potential energy is with a minus sign. And look, we'll just do the simplification, addition. We'll just do the addition and see what is the total energy. So if we just do this addition, so we get k with a minus sign, kz square by 2r. That means, the total energy is equal to, total energy En is equal to the minus of potential, sorry, kinetic energy, minus of kinetic energy. This is the kinetic energy, so minus of kinetic energy. In some cases, you will find out some question that total energy is given, then you will be asked to find out what is potential energy, what is kinetic energy, etc. So there is a relationship. Potential energy will be equal to minus 2 into kinetic energy. Okay, so this is what you remember. And total energy of an electron in particular orbit is actually minus of the kinetic energy. Okay, minus of the kinetic energy. So potential energy is minus 2 into kinetic energy, and total energy is minus kinetic energy. So if sometime total energy is given, then you can find out what is kinetic energy, or if the kinetic energy is given, then you can obviously find out what is the potential energy. Now look, we have got the total energy expression for the total energy En of an hydrogen atom for like an electron in any orbit. So what is that? K z square by 2 into r. Now if we put the value of r, okay, if we put the value of r, what is the expression we get ultimately is 2 pi square mk square e to the power 4 divided by h square, okay, into n square. So this is the thing we get. This is the expression for final expression. So putting the value of r, putting the value of r. What is r? We know what is r, right? What is the expression for the r? So the expression for r is equal to n square, h square divided by 4 pi square mk square, sorry, mk square. So if we put the value over here as r, then we get this thing. Okay, so we get this expression. This is the expression for the total energy of of a hydrogen atom. In fact, there will be z somewhere. So if you put the z is equal to 1, so here z was there already. Okay, so if you put z is equal to 1, then it will be divided of z, and that will give you the total energy of an electron in any orbit. This is nth orbit. For nth orbit, if you want to calculate is equal to 1, then if you put this mk square by h square. So you put the value of h, Planck constant, k is 9 into 10 to the power 9, and then E is the electronic charge, and you know what you get. Finally, you will get minus 13.6 electron volt if you just put all those things and calculate. Okay, so the total energy can be written. See, only n square was not here, so the total energy for hydrogen atom will be given as 13.6 by n square. Okay, in electron volt. So this is for any orbit. For fast Bohr orbit, so you if you want to find out what is the energy for an electron in the fast Bohr orbit, you'll get minus 13.6, n is equal to 1, where n is equal to 1. For second Bohr orbit, how much you get? Second orbit, so this is n is equal to 2, so this will be 4. In fact, you will get minus 3.4. Okay, 4 electron volt. So this state is called fast excited state, because see, this is the lowest energy that hydrogen can have in the fast Bohr orbit. So this state is called ground state. Ground state. Ground state, where the energy of an electron is the least in hydrogen atom. That state is called ground state. So this is the energy when n is equal to 1. That is the energy minus 13.6 electron volt is the least energy of an hydrogen atom, and that will be there in the first Bohr orbit. And look, this is minus 3.4. This is the energy which is greater than this B will be capital. So greater than minus 13.6. So it is actually greater than E1. So these are called, see, this is called ground states, and anything n is equal to 2, 3, 4, whatever you take, these are called excited state. So this is called fast excited state. Excited state. Okay. And if you take n is equal to 3, then it will be called as second excited state. N is equal to 2 is the first, then n is equal to 3 will be second excited state, and third excited state n is equal to 4. So this is how you get energy for various orbits of an hydrogen atom. Now I'll tell you, if you have some electron, see, hydrogen atom has one electron and one proton. So if you have, I'll just clean it here. So En is equal to, we get for hydrogen atom, this is the thing, this is n square. N is the principal quantum number, where n can be, this is ev, n can be 1, 2, 3, etc. Okay, so for hydrogen like atom, like see, helium, it has 2 proton and 2 electron. This has actually mass 4. So 2 proton, 2 electron. So if I have helium singly ionized atom, means 1 electron goes, so you'll get actually 2 proton and 1 electron in that case. So these kind of atoms, like which has only 1 electron in the, so this is hydrogen, it has only 1 electron. So but proton also is 1 in this case, but in some cases proton may be 2 but electron is 1. So this is the case in the orbit. This is the case for singly ionized helium. If you take lithium, lithium has three actually. So you have to take W ionized so that you get one electron in the orbit. So it has three proton actually. Okay, so three proton, but only one electron in the outer orbit. So these are the ions which are called hydrogen-like atom. They have Z number. See, this hydrogen has Z is equal to 1, but this helium has Z is equal to 2, lithium has Z is equal to 3. Okay, but the ions doubly singly ionized, W ionized, triply ionized ions, they are having only one electron in the like in the outer orbit. So these are called. That's why these are called hydrogen-like atom. Hydrogen-like atom. H-like atom. Okay, atom. Hydrogen-like atoms. So for them, in the expression we have just put Z is equal to 1. So for them, what is the total energy for any orbit? How you can write? I'll write and then I'll stop the class. So En will be is equal to minus Z by N square into 13.6 electron volt. Okay, or other way also you can write minus 13.6 into Z by N square will give you the energy of any hydrogen like atom. So suppose energy of ground state helium singly ionized ion. So what will be the energy? It will be minus 13.6 over 1, n is equal to 1, into Z will be 2 actually. So it will be minus 6.8 electron volt if you calculate. I'm sorry, this will be uh, n is equal to 1, right? So yeah, if you just multiply this, you'll get this 12. So this will be your energy in the ground state. Okay, all right. So I'll stop it here. We'll we'll see when we learn about hydrogen spectrum or atomic spectrum. That time we'll discuss again this in detail. So we'll again meet on Wednesday. I'll I'll continue the hydrogen atomic spectra and like various series, Baumar, Pesson, Lyman, etc. And we'll see how Bohr's atomic model is actually able to explain various spectral series also. Obviously, this Bohr's orbit also has certain drawbacks, certain limitations. Those also we'll discuss in the next class. Okay, bye for today.